Alright, today we're going to have a look at proof by contradiction. Now, proof by contradiction is one of my favourite methods of proof, and it sometimes can look a bit spooky and out there, and it also introduced one of my favourite proofs ever, which is to prove that root 2 is irrational. So, proof by contradiction is a form of indirect proof, and the basic idea is to assume that the provided statement is false and then show that this assumption leads to an absurd and impossible result. So if the initial assumption was false and our result is absurd and false, that means the initial statement must be true. So prove by contradiction that if n is an odd integer, then n squared is odd. So I think we've proven this a few times. I think we've proven this by direct proof. We've proven it by contraposition, and now we're going to prove it by contradiction. So we're going to come up with some absurd assumption and then see if that assumption ends up falling out. So let's suppose that if n is odd, so that's what we're trying to, we're assuming that n is odd, but instead of saying that n squared is even, that n squared is odd, we're going to say then n squared is, instead of odd, we're going to say instead it's even. Okay, so let n equal 2k plus 1, so if n is 2k plus 1 for some integer k, well then n squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 2 times by 2k squared plus 2k plus 1. But this is odd, which is odd. Right. Now, often in these proofs, we might label our assumptions. Sometimes people use little asterisks as our assumption. And if this is odd, then that means our assumption is wrong. So this contradicts our assumption. This contradicts our assumption. So if our assumption is wrong, therefore the original statement is true. Therefore, the original statement again, so proof by contradiction involves looking at our question, coming up with some assumption that is false, and then proving that that false assumption is false, which means the original statement is true. Okay. These questions I think are really cute. I love them, and it's really where proof by contradiction comes to shine. So prove that root 2 plus root 3 is less than root 10 by contradiction. So let's suppose that the opposite is true. Let's suppose that root 2 plus root 3 is greater than or equal to root 10. Well, that would imply that root 2 plus root 3 squared is greater than or equal to 10. What we're trying to do here is we can't really work with irrational numbers because without a calculator, we don't know what these irrational numbers are. So we're going to get rid of them by squaring them. Really the only way to get rid of a square number is by squaring it. So if we expand that, we're going to have 2 plus 2 root 6 plus 3, and we're saying it's greater than or equal to 10. So subtracting the 2 plus 3 to the other side, we're saying that 2 root 6 is greater than or equal to 5, And if we square both sides, we're going to get 4. If we square both sides, what do we get? 2 root 6 is greater than 5. If we square both sides, if we square 2 root 6, we get 24. And if we square 5, we get 25. So that's telling us that 24 is greater than or equal to 25, which is not true. So again, this is where contradiction really becomes obvious. 24 is not greater than 25. So this is a contradiction. So therefore the original statement must be true. Root 2 plus root 3 has to be less than root 10. So if this assumption is false, because it's the opposite of the original question, then the original thing has to be true. Okay. Here we go to my favorite proof of all time. I think this type of proof is even cuter than induction. And I don't know, it's just really nice. Proving that root 2 is irrational. So, again, we're proving by contradiction, so let's suppose that it's rational. Let's suppose root 2 is rational. Well, if root 2 is irrational, the definition of a rational number is that it can be written as a fraction. So that means root 2 could be expressed as a fraction p over q. Now, we might say that, we can also say that, okay, every single fraction can be simplified all the way down until we can't simplify it anymore. So we might say that this fraction is a fraction in its most simple form. So p and q are integers with no common factors. Except 1. So p and q are integers with no common factors except 1. So that's going to be our assumption there. So what we're saying is that p over q, all we're saying is it's the most simple form of our rational number root 2. Okay. Let's square this, for example, though. So let's go root 2 equals p on q. Let's square each side. So that would tell us that 2 is equal to p squared over q squared, which is telling us that 2q squared is equal to p squared. Okay, now we know that 2q squared is even because we're multiplying it by 2. That is also telling us that since it's equal to p squared, then p squared is even. And that's because 2q squared is even, or 2q squared is equal to p squared. Now, if you square root an even number, you get another even number. So p is even. So we've decided that p is even. Why don't we say then, therefore, if p is even, then let p equal to 2k, and that's because p is even for some integer k. So, however, we know that p squared is equal to 2q squared, so p squared would be 4k squared. But we know that p squared is equal to 2q squared, so q squared, so 2q squared is equal to 4k squared, and that would tell us that q squared is equal to 2k squared. Now, that would tell us that q is even, because if you square root, if you are saying that q squared is equal to 2k squared, since 2k squared is even, that's telling us that q squared is even, and if you square root q squared, you get another even number, because if you square root an even number, you get another even number. So that's telling us q is even. Now that's a problem, because if q is even and p is even, so we've said that p is even, we've also said that q is even, so p on q cannot be in its most simple form, as p and q have a common factor of 2. So our assumption was that p on q is a fraction in its most simple form, but we've just said that p and q are both even. That doesn't make any sense, because if you've got an even number over an even number, you can take out a factor of 2 and cancel those 2's. So this is a contradiction. Therefore, root 2 is irrational. Cute. I love that question there. I think it's one of them. It's like a spooky proof, and you kind of get to this absurd thing at the end that then proves that this weird number is irrational. I don't know, I really like it. Okay. So last question by contradiction, we're going to say, okay, if 5n plus 3 is odd, then n is even. So let's go, suppose 5n plus 3 is odd. Suppose if 5n plus 3 is odd, then n is even. Okay, so not even, that's just what the question was. We want to prove by contradiction, then n is odd. So we've got our original statement, and then we're going to come up with some sort of statement that's false. So instead of n being even, we're going to say n is odd. So these proof by contradictions, we always get the original thing and then kind of a second thing, and we say, kind of take the opposite of that. So in this one, the original thing was root 2 and the second thing was irrational. The opposite of irrational is rational. Here, the first thing is 5n plus 3 is odd. The second thing is n is even. So we're going to say, what's the opposite of even? It's being odd. So we're going to suppose that this is true. Now that would mean that n is equal to 2k plus 1 because it's odd. So this is for some integer k. Now, we're going to say, okay, what's 5n plus 3 then? 5n plus 3, well, that's going to be 5, 2k plus 1, plus 3. And if we expand all of that, we're going to get 10k plus 8, which unfortunately, we get 2 times 5k plus 4. This is even, which is even. That's a problem there. That contradicts our assumption. So this, we might put an asterisk up here. This contradicts our asterisk. So therefore, 5n plus 3 is odd. If 5n plus 3 is odd, then n is even. Right, and that is the lovely proof by contradiction. Thank you.